Episode 23, titled 2.2 Spot Duplication, Redundancy, Outliers, Completeness, Validation Issues. Quality checks are treated as the guardrails that keep analysis meaningful and keep stakeholders willing to trust what the numbers say. Data quality is not about making a dataset look tidy, because a tidy dataset can still be wrong in ways that matter, such as counting the same transaction twice or quietly losing a required identifier during a merge. When quality checks are skipped, the damage often shows up later as a debate over whose report is correct, even though everyone used the same source, and that is a costly way to learn. This episode builds a practical lens for protecting meaning, so the dataset reflects reality closely enough that conclusions stay stable when someone asks, "Are we sure?" Duplicates are one of the fastest ways to inflate results, and the cleanest way to detect them starts with the fields that define uniqueness. A good uniqueness test usually combines a key, a timestamp, and a small set of matching fields that should not repeat together if the record is truly new, such as an account identifier paired with an event type and a moment in time. When keys are imperfect, timestamps help identify suspicious repeats, like two identical events occurring within a time window that is physically unlikely, which often indicates replay, retry behavior, or ingestion duplication. Matching fields add confidence by showing whether the repeated records are truly identical or merely similar, which matters when distinguishing a genuine repeat action from a system artifact. The core idea is that duplicates are best detected by modeling what one real thing looks like in the business process, then testing whether the data violates that expectation. It helps to separate duplication from redundancy because overcleaning can remove legitimate information and create new errors. Duplication is multiple records representing the same real-world event or entity, which should be counted once for most analytical purposes. Redundancy is repeated information that is intentionally present in multiple places, such as a customer email stored in a customer table and copied into a transaction record to support point-in-time reporting, audits, or historical accuracy. Redundancy can look wasteful, but it often exists to preserve context, support performance, or maintain a trail of what was known at the time of the transaction. When redundancy is mistaken for duplication, analysts may drop fields or records that are needed to interpret the data correctly, and the dataset becomes cleaner but less truthful. Outliers are a different kind of quality risk because they can be either a rare truth worth investigating or a measurement defect that distorts summary statistics. Finding outliers starts with comparing values to typical ranges, but typical should be defined within meaningful groups rather than only across the entire dataset, because what is extreme for one segment may be normal for another. A transaction amount that looks absurd in a consumer segment may be expected in a business segment, and a duration that looks impossible in a manual workflow may be normal in an automated one. Outliers also show up when a distribution suddenly changes shape, like a new cluster of very high values appearing after a release or a migration, which is often a clue that something about capture or units changed. The professional habit is to treat outliers as questions about measurement and process, not as automatic deletions. Completeness is the quiet foundation underneath almost every analysis, because missing required fields change what a record can represent. Completeness checks focus on whether fields that are required for interpretation exist consistently, such as identifiers, timestamps, currency codes, region markers, or status fields that drive grouping and filtering. A dataset can have a high overall row count and still be incomplete in the sense that a key field is missing in a particular time period, region, or channel, which makes comparisons across those slices unreliable. Completeness is also about consistency in meaning, because a field that is sometimes present but sometimes replaced with a placeholder value can create the illusion of completeness while still hiding unknowns. A strong completeness practice treats required fields as a contract, where required means the analysis cannot safely proceed without understanding and addressing gaps. Validation of formats is a practical way to catch errors early, because many data defects are visible in the shape of the value before they are visible in the math. Email fields can be checked for basic structure, not to prove the address exists, but to catch obvious corruption, like missing separators or illegal characters introduced by parsing. Dates can be validated for plausible ranges and consistent patterns, because swapped month and day formats, impossible dates, and time zone-related shifts can create misleading timelines that still look credible. Identifiers can be validated by length, allowed characters, and leading zeros, because type conversions and trimming operations often alter identifiers in ways that break joins later. Format validation is less about perfection and more about protecting interpretability, so downstream logic does not silently treat malformed values as normal. A transaction scenario makes duplication risks concrete, because duplicate charges are both analytically harmful and operationally serious. A customer might see two charges that appear the same, and the data might reflect two transaction rows with the same amount, the same merchant, and nearly the same timestamp, even though only one purchase occurred. That pattern can come from a retry path where a payment request was replayed, or it can come from a pipeline that ingested the same settlement file twice after a transient failure. The analytical symptom is inflated revenue, inflated transaction counts, and possibly inflated fraud rates if chargebacks follow. And the operational symptom is customer dissatisfaction and remediation workload. In this context, duplicate detection is not a cosmetic cleanup step because it protects both business reporting and customer outcomes by preserving the true count of real transactions. Outliers in transaction data often have a specific smell. They appear as sudden extremes that align with unit changes, scaling mistakes, or software defects rather than with plausible customer behavior. A common example is a value captured in cents but later interpreted as dollars, which creates outliers that are exactly 100 times larger than typical values and can dominate averages. Another example is a bug that drops a decimal point or shifts a currency conversion, creating a cluster of abnormal values that begins at a specific time and affects a specific channel. These defects can be subtle if the dataset spans multiple currencies or segments, because the outliers may hide inside legitimate variation unless grouped comparisons are used. The key professional move is to ask whether the outlier distribution aligns with a system boundary, such as a release date, a region, a device type, or a vendor feed, because alignment often points to root cause. Joining related datasets introduces another quality dimension, referential integrity, which is the expectation that keys used to relate tables actually match in consistent ways. When a transaction table references a customer identifier, the analysis often assumes every transaction has a valid customer record, or at least that missing customer links are rare and understood. If referential integrity breaks, aggregates by customer segment can shift, and counts can drop or duplicate depending on join logic, which changes conclusions without changing the underlying business reality. Failures can come from key formatting differences, missing leading zeros, type mismatches, or delayed upstream updates where one dataset lags behind another in time. Referential integrity checks protect meaning by confirming that relationships implied by the schema hold in the data, so joins do not become hidden filters. Validation rules themselves need ownership
because a rule is only useful if it is defined consistently and maintained as systems evolve.
A rule might state that a transaction amount must be non-negative, that an email field must follow a particular format, or that a timestamp must fall within a plausible window. But those rules should come from someone accountable for the business definition and system behavior. When rules are defined informally by analysts in isolation, different reports can encode slightly different versions of the same rule, creating conflicts that look like analytical disagreement, but are really definition drift. Tracking who defines each rule and why it exists makes the rules defensible, and it also makes it easier to update them when a product feature changes or a new region introduces legitimate exceptions. In practice, validation rules work best when they are treated as part of the data contract rather than as ad hoc cleanup logic. Fixing issues at the source is the most durable form of quality improvement because downstream filters can hide defects without removing their cause. If duplicates originate from a retry mechanism that does not produce idempotent identifiers, filtering duplicates in the reporting layer may improve a dashboard while leaving customers exposed to double charges and leaving reconciliation teams with ongoing pain. If outliers come from unit confusion, trimming outliers in analysis may stabilize averages while allowing incorrect values to flow into billing, risk models, or audits. Source fixes also reduce the need for complex logic in every downstream use case, which lowers the chance that one team applies the right fix while another team forgets and repeats the error. The educator's perspective is that downstream cleanup is sometimes necessary for continuity, but it should be paired with an upstream plan so quality improves over time rather than being perpetually patched. After cleaning or correction, rerunning checks is what turns quality work into evidence of improvement rather than a one-time belief. When duplicates are removed or deduplicated, record counts should change in a way that matches expectations, and key metrics should shift predictably rather than mysteriously. When outlier handling is applied, distribution shape should become more plausible, but the change should also be explained, because a large shift can signal that legitimate rare events were mistakenly removed. Completeness and referential integrity should be measured again after transformations and joins, because cleaning steps can introduce new nulls or new mismatches if types or keys are altered. This recheck step is where quality becomes measurable because it proves that the dataset now behaves closer to the underlying process it represents. A short quality scan routine is most effective when it is repeatable and lightweight, so it can be applied consistently rather than only during crises. The routine begins by scanning for duplicates with a clear uniqueness definition tied to business meaning, then checking whether repeated rows are true duplicates or intentional redundancy that preserves context. It continues by reviewing outliers within meaningful groups, looking for extremes that align with system boundaries like time, region, or channel, which often reveals unit shifts or defects. It then confirms completeness of required fields and validates the basic formats of dates, emails, and identifiers so that joins and time-based analysis remain stable. Finally, it checks referential integrity across related datasets and records the validation rules that were applied, which keeps future comparisons defensible when someone asks why a number changed. The conclusion of episode 23 is to choose one quality metric to monitor weekly, because steady monitoring prevents quality problems from becoming surprises that derail analysis later. A good weekly metric is one that reflects a meaningful risk, such as a duplicate rate for transactions, a completeness rate for a critical identifier, an outlier rate beyond a plausible threshold, or a referential integrity match rate for a key join. The purpose is not to chase perfection, but to detect drift early, especially after releases, vendor changes, or pipeline modifications that can alter data shape without obvious warnings. When that metric is tracked consistently, it becomes easier to connect quality signals to real-world causes and to prioritize fixes where they protect the most trust. Over time, that habit turns quality checks into a normal part of analysis, which is exactly how meaning stays protected and results stay credible. Thanks for listening. For more audio courses, daily newsletters, and more, please visit baremetalcyber.com.